The nucleus is the very dense region consisting of protons and neutrons at the center of an atom. It was discovered in 1911 as a result of Ernest Rutherford's interpretation of the 1909 Geiger-Marsden gold foil experiment performed by Hans Geiger and Ernest Marsden under Rutherford's direction. The proton-neutron model of nucleus was proposed by Dmitry Ivanenko in 1932. Almost all of the mass of an atom is located in the nucleus, with a very small contribution from the electron cloud. The diameter of the nucleus is in the range of 1.75 fm, 1.75 1015 m, for hydrogen, the diameter of a single proton, to about 15 fm, for the heaviest atoms, such as uranium. These dimensions are much smaller than the diameter of the atom itself, nucleus, plus electron cloud, by a factor of about 23,000, uranium, to about 145,000, hydrogen. The branch of physics concerned with studying and understanding the atomic nucleus, including its composition and the forces which bind it together, is called nuclear physics. The nucleus was discovered in 1911 as a result of Ernest Rutherford's efforts to test Thomson's plum-pudding model of the atom. The electron had already been discovered earlier by J.J. Thomson himself, and knowing that atoms are neutral, Thomson postulated that there must be a positive charge as well. In his plum-pudding model, Thomson stated that an atom consisted of negative electrons randomly scattered within a sphere of positive charge. Ernest Rutherford later devised an experiment that involved the deflection of alpha particles at a thin sheet of metal foil. He reasoned that, if Thomson's model were correct, the immense alpha particles would easily pass through the foil with very little deviation in their paths. To his surprise, many of the particles were deflected at very large angles. Because the mass of alpha particles is about 8,000 times that of an electron, it became apparent that a very strong force was present that allowed the particles to be deflected. He realized that the plum-pudding model could not be accurate, and that the deflections of the alpha particles could only be caused by a center of concentrated charge that contained most of the atom's mass. Thus, the idea of a nuclear atom, an atom with a dense center of positive charge, became justified. Etymology. The term nucleus is from the Latin word nucleus, a diminutive of nux, nut meaning the kernel, i.e., the small nut inside a watery type of fruit, like a peach. In 1844, Michael Faraday used the term to refer to the central point of an atom. The modern atomic meaning was proposed by Ernest Rutherford in 1912. The adoption of the term nucleus to atomic theory, however, was not immediate. In 1916, for example, Gilbert and Lewis stated, in his famous article The Atom and the Molecule, that the atom is composed of the kernel and an outer atom or shell. Nuclear makeup. A figurative depiction of the helium-4 atom with the electron cloud in shades of gray. In the nucleus, the 2 protons and 2 neutrons are depicted in red and blue. This depiction shows the particles as separate, whereas in an actual helium atom, the protons are superimposed in space, and most likely found at the very center of the nucleus. And the same is true of the 2 neutrons. Thus, all 4 particles are most likely found in exactly the same space, at the central point. Classical images of separate particles fail to model known charge distributions in very small nuclei. A more accurate image is that the spatial distribution of nucleons in helium's nucleus, although on a far smaller scale, is much closer to the helium electron cloud shown here than to the fanciful nucleus image. The nucleus of an atom consists of protons and neutrons, 2 types of baryons, bound by the nuclear force, also known as the residual strong force. These baryons are further composed of subatomic fundamental particles known as quarks bound by the strong interaction. Which chemical element an atom represents is determined by the number of protons in the nucleus. Each proton carries a single positive charge, and the total electrical charge of the nucleus is spread fairly uniformly throughout its body, with a fall-off at the edge. Major exceptions to this rule are the light elements hydrogen and helium, where the charge is concentrated most highly at the single central point, without a central volume of uniform charge. This configuration is the same as for one's electrons in atomic orbitals and is the expected density distribution for fermions, in this case, protons, in one state without orbital angular momentum. As each proton carries a unit of charge, the charge distribution is indicative of the proton distribution. The neutron distribution probably is similar. While protons define the entire charge of a nucleus, and, hence, its chemical identity, neutrons are electrically neutral, but contribute to the mass of a nucleus to the same extent. Neutrons explain the phenomenon of isotopes, varieties of a chemical element which differ in atomic mass. Protons and neutrons. Protons and neutrons are fermions, with different values of the strong isospin quantum number, so two protons and two neutrons can't share the same space wave function, since they are not identical quantum entities. They sometimes are viewed as two different quantum states of the same particle, the nucleon. Two fermions, such as two protons, or two neutrons, or a proton plus neutron, the deuteron, can exhibit bosonic behavior when they become loosely bound in pairs. In the rare case of a hypernucleus, a third baryon called a hyperon, with a different value of the strangeness quantum number can also share the wave function. However, the latter type of nuclei are extremely unstable, and are not found on Earth, except in high-energy physics experiments. The neutron has a positively charged core of radius 0.3 fm surrounded by a compensating negative charge of radius between 0.3 fm and 2 fm. The proton has an approximately exponentially decaying positive charge distribution, with a mean square radius of about 0.8 fm. Forces. Nuclei are bound together by the residual strong force, nuclear force. The residual strong force is a minor residuum of the strong interaction which binds quarks together to form protons and neutrons. This force is much weaker between neutrons and protons because it is mostly neutralized within them, in the same way that electromagnetic forces between neutral atoms, such as van der Waals forces, that act between two inert gas atoms, are much weaker than the electromagnetic forces that hold the parts of the atoms internally together, for example, the forces that hold the electrons in an inert gas atom bound to its nucleus. The nuclear force is highly attractive at the distance of typical nucleon separation, and this overwhelms the repulsion between protons, which is due to the electromagnetic force, thus allowing nuclei to exist. However, because the residual strong force has a limited range, because it decays quickly with distance, see Yukawa potential, only nuclei smaller than a certain size can be completely stable. The largest known completely stable, e.g., stable to alpha, beta, and gamma decay, nucleus is lead-208, which contains a total of 208 nucleons, 126 neutrons, and 82 protons. Nuclei larger than this maximal size of 208 particles are unstable, and, as a trend, become increasingly short-lived with larger size, as the number of neutrons and protons which compose them increases beyond this number. However, bismuth-209 is also stable to beta decay, and has the longest half-life to alpha decay of any known isotope, estimated at 1 billion times longer than the age of the universe. The residual strong force is effective over a very short range, usually only a few Fermis, roughly 1 or 2 nucleon diameters, and causes an attraction between any pair of nucleons. For example, between protons and neutrons to form an p-deuteron, and also between protons, and neutrons and neutrons. Halonuclei and strong force range limits. The effective absolute limit of the range of the strong force is represented by halonuclei such as lithium-11 or boron-14, in which dineutrons, or other collections of neutrons, orbit at distances of about 10 Fermis, roughly similar to the 8 Fermi radius of the nucleus of uranium-238. These nuclei are not maximally dense. Halonuclei form at the extreme edges of the chart of the nuclides, the neutron drip line and proton drip line, and are all unstable with short half-lives, measured in milliseconds. For example, lithium-11 has a half-life of less than 8.6 milliseconds. Halos in effect represent an excited state with nucleons in an outer quantum shell which has unfilled energy levels below it, both in terms of radius and energy. The halo may be made of either neutrons N, or protons pp. Nuclei which have a single neutron halo include 11b and 19c. A two-neutron halo is exhibited by 6e, 11e, 17b, 19b, and 22c. Two-neutron halo nuclei break into three fragments, never two, and are called Borromine nuclei because of this behavior, referring to a system of three interlocked rings in which breaking and airing frees both of the others. 8e and 14b both exhibit a four-neutron halo. Nuclei which have a proton halo include 8b and 26p. A two-proton halo is exhibited by 17ne and 27s. Proton halos are expected to be more rare and unstable than the neutron examples because of the repulsive electromagnetic forces of the excess proton s. Nuclear models. Although the standard model of physics widely believed to completely describe the composition and behavior of the nucleus, generating predictions from theory is much more difficult than for most other areas of particle physics. This is essentially because perturbation theory, the widely used mathematical tool, is not applicable to quantum chromodynamics, the theory of the strong force, at the energy scales relevant to the nucleus. As a result, experiments have historically been compared to relatively crude models which are necessarily imperfect. None of these models completely explain experimental data on nuclear structure. The nuclear radius, r, is considered to be one of the basic quantities that any model must predict. For stable nuclei, not halonuclei, or other unstable distorted nuclei, the nuclear radius is roughly proportional to the cube root of the mass number, A, of the nucleus, and particularly in nuclei containing many nucleons, as they arrange in more spherical configurations. The stable nucleus has approximately a constant density, and therefore the nuclear radius r can be approximated by the following formula, where A equals atomic mass number, the number of protons Z, plus the number of neutrons N, and R0 equals 1.25 Fm equals 1.25 1015 m. In this equation, the constant R0 varies by 0.2 Fm, depending on the nucleus in question, but this is less than 20% change from a constant. In other words, packing protons and neutrons in the nucleus gives approximately the same total size result as packing hard spheres of a constant size, like marbles, into a tight spherical or almost spherical bag. Some stable nuclei are not quite spherical, but are known to be prolate. Liquid drop models. Early models of the nucleus viewed the nucleus as a rotating liquid drop. In this model, the trade-off of long-range electromagnetic forces and relatively short-range nuclear forces together cause behavior which resembled surface tension forces in liquid drops of different sizes. This formula is successful at explaining many important phenomena of nuclei, such as their changing amounts of binding energy as their size and composition changes. See semi-empirical mass formula, but it does not explain the special stability which occurs when nuclei have special magic numbers of protons or neutrons. Shell models and other quantum models. A number of models for the nucleus have also been proposed in which nucleons occupy orbitals, much like the atomic orbitals in atomic physics theory. These wave models imagine nucleons to be either sizeless point particles in potential wells, or else probability waves, as in the optical model frictionlessly orbiting at high speed in potential wells. In the above models, the nucleons may occupy orbitals in pairs, due to being fermions, which allows to explain even/odd Z and N effects well known from experiments. The exact nature and capacity of nuclear shells differs from those of electrons in atomic orbitals, primarily because the potential well, in which the nucleons move, especially in larger nuclei, is quite different from the central electromagnetic potential well which binds electrons in atoms. Some resemblance to atomic orbital models may be seen in a small atomic nucleus, like that of helium-4, in which the two protons and two neutrons separately occupy one's orbitals analogous to the one's orbital for the 2 electrons in the helium atom and achieve unusual stability for the same reason. Nuclei with 5 nucleons are all extremely unstable and short-lived, yet helium-3, with 3 nucleons, is very stable even with lack of a close 1s orbital shell. Another nucleus with 3 nucleons, the triton hydrogen-3, is unstable, and will decay into helium-3 when isolated. Weak nuclear stability with 2 nucleons Np in the 1s orbital is found in the deuteron hydrogen-2, with only 1 nucleon in each of the proton and neutron potential wells. While each nucleon is a fermion, the Np deuteron is a boson, and thus does not follow Pauli exclusion for close packing within shells. Lithium-6 with 6 nucleons is highly stable without a close second 1p shell orbital. For light nuclei with total nucleon numbers 1 to 6, only those with 5 do not show some evidence of stability. Observations of beta stability of light nuclei outside closed shells indicate that nuclear stability is much more complex than simple closure of shell orbitals with magic numbers of protons and neutrons. For larger nuclei, the shells occupied by nucleons begin to differ significantly from electron shells, but nevertheless, present nuclear theory does predict the magic numbers of filled nuclear shells for both protons and neutrons. The closure of the stable shells predicts unusually stable configurations, analogous to the noble group of nearly inert gases in chemistry. An example is the stability of the closed shell of 50 protons, which allows to have 10 stable isotopes, more than any other element. Similarly, the distance from shell closure explains the unusual instability of isotopes which have far from stable numbers of these particles, such as the radioactive elements 43, technetium, and 61, promethium, each of which is preceded and followed by 17 or more stable elements. There are, however, problems with the shell model when an attempt is made to account for nuclear properties well away from closed shells. This has led to complex post hoc distortions of the shape of the potential well to fit experimental data, but the question remains whether these mathematical manipulations actually correspond to the spatial deformations in real nuclei. Problems with the shell model have led some to propose realistic 2-body and 3-body nuclear force effects involving nucleon clusters, and then build the nucleus on this basis. 2 such cluster models are the Close-Pax-Farron model of Linus Pauling and the 2D-Ising model of McGregor. Consistency between models. As with the case of superfluid liquid helium, atomic nuclei are an example of a state in which both 1. Ordinary particle physical rules for volume, and 2. Non-intuitive quantum mechanical rules for a wave-like nature apply. In superfluid helium, the helium atoms have volume and essentially touch each other, yet at the same time exhibit strange bulk properties, consistent with a Bose-Einstein condensation. The latter reveals that they also have a wave-like nature, and do not exhibit standard fluid properties, such as friction. For nuclei made of hadrons which are fermions, the same type of condensation does not occur, yet nevertheless, many nuclear properties can only be explained similarly by a combination of properties of particles with volume, in addition to the frictionless motion characteristic of the wave-like behavior of objects trapped in Erwin Schrödinger's quantum orbitals.